in Braga, Portugal. And it's part of a project called Smartix, which is a technological platform for intelligent monitoring of open industrial spaces. This work focuses on two issues. One of them is to turn industrial spaces more efficient and intelligent, and the other is the rise of self-supervised learning. So we grabbed two use cases of this project where we want to turn it more efficient in industrial spaces. Nowadays, it is done manually or with CCTV cameras. And so it relies on humans, which happens to have lots of human errors. If the space is very big, you have lots of cameras to monitor, and sometimes it takes too long to get to the problem and fix it. And so what we want is to put a camera to grab real-time information and classify it in real time, to make it more effective and to send a trigger straight away so someone can see the situation and fix it. The other question is about self-supervised learning. Well, this is currently done in some situations, but in a supervised manner. How is that? So we have to label a lot of data, and sometimes it can be very time-consuming and expensive. And in this case, in industrial spaces, it's very hard to acquire a lot of images because you have just that scenario, and the correct image is basically the same. And so self-supervised learning helps in these issues. So what is self-supervised learning? It's a learning technique where the data is automatically labeled due to the relationships between the images, the similarity that they have. And due to that similarity, they can divide them into the space without needing to label it. And in this way, it learns a lot of semantic and high representations of the data. There are two types, pretext task and contrastive learning. I will speak very shortly about each of them and then pass to the model used. The motivation behind this was people, well, as babies, our first interaction, the way we learn before having our parents as giving us supervised signals, is we learn for observation. We look and we can differentiate things. And so the main idea of SSCL is to, by looking at the data, seeing the similarity, be able to differentiate it. And then we can use that information and use it in other things. And this is where the part of the adults come. Every new task we do it with previous information that we gained during our life. And so if we train a model and in a certain space, we can grab that information from that space and apply it to a similar space without wasting too much training time and make it more effective. Some people call this the dark matter of AI, which is our common sense. The initial states of SSCL were pretext tasks, where we gave a task for a model, and by solving the task, he could extract relative features that we could then use to other tasks, such as classification, detection, and segmentation. And those intermediate layers will encode high-level semantics that will be useful for those other tasks. Examples of this are, for example, painting an image, a grayscale image to a color image. By painting it, he recognized edges and different parts of the image, which will then help in the downstream tasks. Despite the good results with pre-state tasks, there was still a big gap between supervised learning and so then appears contrastive learning, which the main idea is you give various images or the same image to a model, and that model can then aims to minimize the distance between those images that are similar and separate the images that are non-similar. And so in this way, without excessive training and without having to label every single image, he can then see the similarity between the images and join them together in the feature space and separate from different images. After a long study of different types of self-supervised learning methods, at the time, SWAB was the one that had better results. And so it was the model used in this work. SWAB means swapping assignments between multiple views of the same image. This model was proposed by Mrs. Carone. It's an excellent paper that is referenced in my paper. If you want to know more detail, I'll just give a brief explanation. And so initially, we give the model a batch of images, and each image we apply multi-crop. So that image is cropped randomly, and we have two high resolution image and low resolution images. This makes the model learn more features and makes the scale invariant, which helps even in other self-supervised learning models. And to those images, random augmentation is applied, such as random flips, blur, etc. Those views are then passed to an encoder, which in our case is a ResNet 50, that follows a projection head and outputs an embedding vector, denoted by Z. That is the representation of those images as a vector. These vectors are then mapped to a set of k-trainable prototypes. So each image will be part of certain features that are the Cs, and then this mapping happens between all the images, and that is denoted by Q. Q is then optimized with a synchron algorithm to maximize the similarity between those features and the prototypes, using this function where H is a cross-entropy function, and epsilon just is a parameter that takes the smoothness of the mapping. And so this is iterated, and once we find an optimal solution, we apply a soft prediction copy with this loss function, which is the loss function between the features Z and the codes. What happens here? If two images are similar, and the codes must be similar too because they are from the same image. And so if they are similar, then a code should be able to predict the feature vector from the other image. And this is where the name comes from, swapping assignments between multiple views. This is the updating backpropagation and makes it not so hard to train. We applied SWAP to 3 datasets. The first one is the flowers, which has 3,670 images. This was just for initial training to have a big dataset, because the industrial datasets that we acquired are very small due to the reasons I mentioned earlier. And so this one has 5 classes, and the other one is the boxes dataset. This is one of the industrial datasets that we tried to mimic. What happens in the industrial space is that we have a slope, and the boxes fall down. And we can see here that the correct position of the boxes is 1, these 2 images, and incorrect is 0. What happens in these industrial spaces is that sometimes they get misplaced, and then the production has to stop until someone finds where it got misplaced and fixes it. In this way, we make it more quick and effective by in real time saying there's something happening here for an alert to be sent, and someone goes and fixes it. Also, as I said, it's very hard to grab these images because we only have these boxes. And as you can see in 0, there's a box that isn't supposed to be there. And that is another anomaly. The other data set is the bookcase data set. So we created this data set that has 4,597 images, and there are 2 classes, empty and full. This is also to mimic another scenario where we have pieces of cloth that go into little shelves. And normally, at the moment, someone goes there and checks by himself if it is empty or not. So what we want is in real time, when that is 0, so when it is empty, so a trigger can be sent and an AGV can go and fill it up. So we train SWAP with 2 high-resolution images and 3 low-resolution images. We use ResNet 50 as a backbone, and 2 dense layers with ReLU activation function, 15 prototypes, and mini-batch SGD. So for the first 2 datasets, flowers and boxes, we trained 85% was used for training, and then we just put in the classifier and validated the rest of the 15%. These were the initial results for flowers. As you can see, the first one didn't have very good results because we initialized with random weights, but then the rest were initialized with the ImageNet weights, and it was much more efficient. The variation of these results are due to lowering the learning rate and increasing the the epochs. And so we could see that C was the best result. This wasn't optimized because it wasn't the focus of our work. We then used the parameters used in the flowers and applied to the bookcase. And we got quite good results, 98.8% accuracy, where he just failed 6 images. Compared to the supervised version, he went down a bit. However, we still achieved quite good results compared to. Then we tried to apply some of the books data set. Here we just don't transfer learning. So we used what we learned from the bookcase data set and applied it, just training the last linear layer of the boxes and tried to figure out the results. We divide in 70-30 because this data set was very small, and if we divide in 85-15, we would only have 17 images for validation, and it wouldn't be enough to see the performance of the model. And in this case, we can see that the accuracy of the self-supervised paradigm was 100% compared to the supervised version was 77%. This happened because there were very few images for the model to learn effectively the difference between the anomaly and the correct image. However, when given a new image or a different background, the model failed to predict it correctly. This happened because the SWOG was only trained with two classes, very small comparative to the authors that trained on ImageNet, which has 1,000 classes and a variety of images, which helps him be more feature relevant. And so the conclusion was that it achieved good accuracy despite not generalizing well. And what we are doing at the moment is creating a big industrial data set with previous projects like defects on leathers and putting it all together to create a big data set as ImageNet but in industrial matter. And so that we can then apply it and see the results and expect it to be very good, and just needing to train once that big, huge model and apply and transfer learning for the rest of the industrial data sets. Thank you for your attention.
Thank you very much. Very interesting presentation. You can stay here. Maybe I don't know if there are questions from the audience or from
online. There is no
question. So maybe I have a couple of questions which are very interesting work. I wonder, the first question is it possible that you encounter some cases where you can imagine what kind of situations could occur? So it's not that only the learner has to learn what's going on, but you can complement this information with some kind of textual description of what's going on, like kind of zero-shot learning where you couple the visual information that the learner has to learn with some textual information which describes the context. So you inject some kind of information already to the learner that facilitates the task.
We haven't done that yet, but I do think it works because there is also work with SSCL with NLP, and there has been some studies in joining both of them. And so I think it does, but we just focus on images. So yeah.
Okay, so it's great. And the second thing that I was wondering is this kind of applications. Is it meant to be only for detecting, for example, the misplacement of books or pieces of boxes, or you can imagine to use it or to modify to use it, for example, to detect, I don't know, I was thinking about either some preemptive fault detection, so if there's some piece which is going maybe to break soon and you already can see from some kind of image.
Yes, it does work the same. You just have to give it any detect those features inside it. So we actually have one that has to also detects the defect in leather. And he also does that quite well.
Okay. And also I think maybe I can think about other different kinds of let's say industrial applications. Like for example, I was once confronted with the problem of the commissioning of buildings where there is a lot of material that can be still reused, but it has to be stored selectively. So you cannot mix glass with the stones, certain material or aluminum. So you have to select it correctly. But oftentimes, let's say the workers on the site, they don't do this very meticulous work. So the materials are all mixed, but still separable. If preemptively, let's say, soon enough, there is maybe a machine or a camera which identifies by the shape, the size, the color. For example, that the material, which kind of material is in the damper. So maybe this could be also something.
Yes, I think it would work very well. And it's helpful because most people don't want to also have to label everything. And so if we train on a general basis, it can almost detect everything, separating itself in the feature space. And so it works very well.
Thank you very much.
One other question, actually. This is self-supervised learning with classification problems.
Yes.
And did you see some application for the regression problems, or it's only for classification?
I just worked with classification. There was some for detection and segmentation, but regression.
Yeah. Thank you very much for the
Thank you.
Thank you.
So our next presentation is Riyad Agnew, a quantum annealing solution to the job shop scheduling problem. So the floor is yours. You have 15 minutes to present.
Okay, thank you.
Let's find that one. Which is yours? Is it this one?
Yes, I guess.
No. This one?
Yeah.
Just give me a second. It doesn't want to do this, so. Is that okay with you?
Yeah. Okay, thank you. So hello everyone, I'm Riyad Agnew from Luxembourg Institute of Science and Technology, and this is a joint work with Samuel Deleplan from Clunia in France, in Lille. So it's about how to use quantum computers to solve some kind of optimization problems, and namely job shop scheduling problems. So before to start, just to scope the study and the work we are doing. So there are different applications of quantum technologies. So you can try to do some quantum simulations, some quantum communications. There is quantum sensing as well. And here we are interested by quantum optimization. So the idea is try to use quantum computers to try to solve some NP-hard problems, like traffic management scheduling problems. You may know also that there are different types of quantum technologies, or quantum computers. Some machines that are called universal quantum computers that are using some gates inside the processing. And here we are more interested by some analogies quantum computers, like the one proposed by the company D-Wave. So, as I said, there are various technologies to build quantum computers. So the most advanced ones are superconducting qubits, traptions as well. At least we are trying to develop some qubits based on spin qubits. So the talk is organized as follows. I will introduce the scheduling problems, then I will speak about how to model the problem, and I will give an overview of solution methods that are proposed in the literature to solve scheduling problems, and with some final take-home message. So as I said, there are two types of computers, and then two types of ways to program the quantum computer. So the classical one, which is to apply some operations on the qubits, which you can call circuit programming. And there's also the quantum annealing method, which allows to solving some larger size problems. So, and these annealing, quantum annealing machines are specialized, dedicated to optimization problems. In terms of types of algorithms for optimization, we have some exact methods like the Grover search and some meta-heuristics like QA/OA and quantum annealing. And in general, those methods require kind of modeling that uses quadratic modeling. So some machines can cope, or some environments can cope with constraints models. And here we are more interested by unconstrained model, which are called QBOs. So the job shop scheduling problem can be defined as follows. We have to schedule a number of operations of jobs on a given number of machines. And the idea is to try to finish as soon as possible to execute those jobs. So we have to find the right sequence, the best sequence for each machine. And so it's a NP-hard problem, which is if you have more than 2 machines and 2 jobs. And a special case of this job shop scheduling problem is a flow shop scheduling problems where each job visits a machine in a sequence, and machine M1, machine M2, then machine M3. So the main constraints are that each job has its own sequence, its own routine, and each machine can process one operation at a time. So in general, we use the classical, let's say, solvers that answer these optimization problems, use some linear models like this one. So we have to minimize the Cmax, which is the end of the last operation. And then we have the constraint that I was mentioning. We have to wait until we have to schedule one job after another, and we have to start one operation when the previous one is finished. So these are what are called the disjunctive constraints and, let's say, the resource constraints, the two types of constraints. So we have to optimizing the problem aims at finding the right values for the starting time and the starting time for the different jobs on the various machines, so that the Cmax is minimized. So this is in a classical case. If we want to express this as a quadratic problem, then we have to change the two types of constraints I was mentioning. So the constraints that forces the operations to be executed one after the other, and so we make those constraints quadratic, and we also penalize all those constraints and we put them in the objective to make the problem unconstrained. So at the end, we have a quadratic problem with no constraints, and the idea is still to answer to minimize the Cmax plus those constraints. So the only thing is that in this case, we still have some integer values. Here the Cmax is not the binary variables, and what we need for solving this on a quantum machine is to change it so that we have only binary variables. And at the end, only variables where you decide whether it has value 0 or 1. So for that, we can try to remove this constraint, and we modify it by considering another objective, which is not the max span, the end of the last job, but which is the completion of the which correspond to the completion of the job, the sum of the jobs. So with this new model, we have something which is quadratic, unconstrained, and only with binary variables. So this can be used on a quantum computer. So the general solution approach consists in defining these QBO models, and then the solution will just apply some transformation on the qubits, and it will make evolve the objective function until we reach the best value, which corresponds to a state of the machine where the energy is minimal. So this strongly depends on the machine we are using. So it's generally limited in terms of number of qubits and also their precision level. And in D-Wave machines, like the ones we are using, we have also a limit on the connectivity of the qubits between each other. So just a small overview of a solution method developed for solving job shop scheduling problems. So the first paper was developed by Venturelli et al. So they considered, they used D-Wave 2 machines. So it was first generation in 2016. So it has about 500 qubits. And it was used only for problems with n jobs and six jobs and 6 machines. And then their model, the QBO they have proposed, was reused on the other generations of machines, and other authors solved let's say harder problems with the same model. So more recently, we have Carugno et al. Who used the most advanced machines from D-Wave, and they could solve that kind of problem with 4 jobs and 4 machines. And this is how it looks like on the D-Wave interface. And this is also the kind of problems we managed to reach and to solve with the model I have shown. So this is one of Carugno and what we found. So it's limited in terms of jobs and machines, but it's a good first step, let's say. Another type of solution methods are the variational algorithm. So only one attempt has been done. So it was solved on the quantum computer developed by IBM, but it was very limited in terms of number of variables. So they could solve only a very small problem. So I can skip this. And we have also a few papers who tries to, a few studies where the authors try to solve bigger problems using some specialized hardware, like the ones developed by Fujitsu company. So these are kind of simulators. So with this kind of approach, yeah, they can solve some larger size problem. So with what we have done with the Cubo I have presented, we are able to solve scheduling problems on D-Wave machines. Unfortunately, this formulation strongly depends on the number of periods. It's a time-indexed model. So we have to integrate into the solution procedure some ways to define the right time span on which we apply the method. But it's a good first step, let's say. So just to conclude, we have in the literature only a few papers dealing with quantum solutions for scheduling problems. The references are very recent. In any case, we are limited in terms of variables and constraints that we can put into our models. The hybrid approaches seems to be a good way to tackle larger size problem. And yeah, we are working now on better Cubo formulations and better way to handle the penalties in the objective function. And thank you for your attention.
Presentation. Do you have any questions for Yad? Actually, I have two questions. So before you said that I'm not actually aware of the job shop, but you said starting from 2 jobs and 2 machines, it's an NP hard problems. But what are the limitations? The hardware limitation right now, how many jobs and how many machines we can handle right now?
Yeah,
I would say an estimation.
Yeah. In the classical case, just to give you an idea, problems with 10 jobs and 10 machines were considered very hard to solve, even with classical machines, until I would say 3 to 5 years. And now, finding the optimal solution for a problem with 20 jobs and 20 machines is really a hard task, even now.
And regarding the comparison with the traditional methods, is there some advantage regarding the computing time and the sustainability, for instance?
Yeah, this is the most interesting promise, I would say, for the quantum computing technologies is to be able to solve larger size problems in the future, and to reduce as well the computational time and also the energy consumption, because we are in the scale of nanoseconds for solving some problems rather than microseconds on HPCs, for instance.
Thank you. So if there is no other question.
Thank you. So now we stay on quantum machines, and I invite Samuel Delplanque to present solving 3 SAT and MIS problems with analog quantum.
This one, yeah. That one? Oh, great. What? Just see.
Yes, indeed, I will talk about the resolution of a FreeSat problem, but with a very specific method. I try to use the polynomial time reduction to another NPR problem, the maximum independent set. Typically, it's something we use to state the complexity of a problem, but in the specific case where we use quantum computers, it appears it can be a solution to solve a problem more quickly. Here is my outline, but I won't spend a lot of time on the D-Wave machine since Riyad present there. I will talk about my strategy to solve the FreeSat, and we will have some results at the end. So this type of machine is based on quantum annealing. This is not a programmable machine. We cannot develop, for example, a quantum algorithm such as the Grover algorithm. It can handle linear and quadratic expressions, and all the constraints must be relaxed into the objective function as a penalty. So quantum annealing has been proven to be more efficient than the well-known simulating annealing in theory, because to build such a computer is very complicated, of course. And this type of computer, so take QLOS, but also a few parameters, so we'll come back on them later. And we talk about real machines in Canada. D-Wave is a Canadian company, and once we have formulated our QBOs, we send through the cloud the model to optimize. Here, I draw a UML activity diagram to split the different actions we have to do for solving our problem. So here we have a human action. We start with a system to optimize. We can, for example, directly write a mixed integer linear problem. We must reformulate it into a QBO or an Ising model, which is an isomorph of a QBO with -1 + 1 variables. In any case, the computer will transform our QBO or directly work with the Ising model. The bottleneck of such experience is the embedding process. Here I mean the mapping of our QBO's graph to the qubits graph. Here, the qubits graph might have not enough connectivity. I mean by that, the degree of a qubits graph is not enough, and then the QBO finally is transformed into another QBO or Ising model, more complicated, more large, to be solved. If a mapping or embedding is found, the system will replicate several times the quantum annealing, and at the end we will obtain many solutions. Okay, so here you have the three last topologies of the qubit graph in the D-Wave machines, and we can see here in blue a qubit connected to 6 over in a pretty old now topology, a linear one. We have a 6 connectivity. And with more recent machines, like the one we're talking about, the Advantage one, where each qubit is connected to 15 overs. But imagine you have to solve a TSP instance with 20 cities. You need a complete graph. So this connectivity is definitely not enough. So your graph will be modified to a larger graph, and you might have a time to find how to build this graph. Okay, I'll go fast on that. Here you have an example of a max-cut instance from the literature solved with such a machine. Here you have a max-cut graph with around 500 vertices. And finally, we need 3,000 qubits in order to map our instance into the QPU. And this graph is pretty sparse, and the fact to use 6 times more qubits than the number of variables is not so bad. But for more complicated problems, it's definitely a problem. Okay, so this work, the goal is to solve the FreeSat problem on a quantum computer. So today, the analog quantum computers are maybe the most powerful quantum computers, so I chose the D-Wave machines. But the problem of this machine is the topology, like I said, is static, the topology of the qubits graph. And if we try to create a QBO, so a quadratic unconstrained binary optimization model from a FreeSat instance, we will use the different clause of the FreeSat problem And from each clause, we will create an equivalence penalty into the objective function, and we will have a big cubo at the end, since we will have for one given clause something like x1 plus x2 plus x3, not lower but greater or equal to 1, and the relative penalty will be way more complicated than that. We will have a degree 3, 2 quadratized, and at the end, the cubo will be very complicated. So the idea here is to transform a problem into another problem through a polynomial time reduction, and we obtain, with a maximum independent set problem, some constraints with this chain, and the equivalent penalty will be very easy to code. Okay, so shortly, the three-sat problem, it's pretty known, so I'll go fast on that. Through an example, we have 3 clauses here in this example, and we must satisfy each clause by at least one literal, one variable in each clause. For example, the solution v1 equals 0, 0, 0 for v3. Here we have the negation of v3, so we have 1. We satisfy the clause. Negation of 0, it's 1. Negation of 2 is 1 again. So we satisfy the 3 clauses. That's just an example. It's an NPR problem. For the maximum independent set, so we have a graph, and the only rule here is to maximize the number of vertices we select in the set according to one rule. For each given edge, for example, this one, a maximum of one vertex can be selected in the maximum independent set. 7, for example, or no one. We used to model that NPR problem with a linear model with this type of binary vector. Xk for vertex k will be equal to 1 if we select the vertex in the independent set, 0 otherwise. So we try to maximize the number of vertices in this set, and the only one rule for each edge KL, the maximum of 1 can be in the independent set. So that it is very easy to transform in a quadratic constraints. From that constraint, we can write this quadratic XKXL constraint. It's completely equivalent. We can see here, if we select both KL, K and L vertices in the independent set, we do not satisfy the constraint. So at the end, the cubo we obtain, it's pretty easy. We have to minimize this cubo. So we have a minus here for the number of vertices we selected. And we will pay a lambda penalty for each constraint we did not satisfy. Okay, so to make the reduction, we use new variables, yij, the y for the clause, and the j for the original variable from the free set. And yij will be equal to 1 if the vertex ij will be selected in the independent set. How we have the different edges. So first, for each clause, we will have a free vertex click. We will connect all the vertices together. And the second rule is to connect each variable with its negation across the different clauses. For example, for our very simple example above, the free set here, we have a first clause with a negation of v3. It is related to that y13, and we will connect it to its negation v3 here and v3 here. So here and here. So we obtain a new graph, and we optimize the number of vertices we select in the so-called independent set. Okay. So here it's just how we calculate the solution of the free set from the solution of the maximum independent set. It's pretty easy. We take all the variables yij equal to 1, and then we deduce if it's 0 or 1 according to the negation or not we have at the end. So I give that to gain some times. So the general scheme of resolution is the following. We start with the free set instance. We use the polynomial time reduction to the maximum independent set. We formulate the cubo of this maximum independent set instance, we give a QO and few parameters to the quantum machine, and then from the different solutions we obtain, we build a free-sat solution or several. Okay, for our very simple example, it's what we obtain. Here, so we have our QO here, we have three clauses, and if we have three clauses, the optimal solution here will be -3. And we can deduce directly here, we have the optimal since we use a very large lambda penalty. And we can see, for example, in the worst solution here, we did not satisfy one of the constraints because we paid 1,000 penalty because one constraint was not satisfied. Just a remark, something pretty nice in quantum computing. In theory, once you have configured your model, at the moment you have to do the measurement, all the optimal solutions have the same probability to appear. In that case, the fact to run several times the same quantum annealing, even if it's a meta heuristic, in that case here, we obtain all the optimal solutions, which is pretty nice. And from that solutions, we build all the feasible solutions for the free-sat problem, which is the feasibility problem. Here, another experiment with 6 clauses. So we build our MIS graph, INC are the same here, and we try 2 different topologies. The old one, the Chimera one, and a more recent one, the Pegasus one. And we can see, like, from the 6 clauses, we have 18 variables, 3 times the normal number of clauses. And for the old topology, we required 61 qubits, and for the most recent one, I think I clicked here. The best one, the worst one. Most recent here, we need only 31 qubits. Okay, I will practically finish with this slide. I try to solve a more tight instance of the free-sat problem with 11 clauses, so 33 variables, and so we obtain this maximum independent set graph with 33 variables, and here the machine requires 95 qubits. Sadly, we obtain only few optimal solutions, not all of them, but still we succeed to solve this problem. Okay, but at the end, even if we succeed to solve more instances than the typical free-sat formulation through a QO, we want to pass through this decomposition. It remains a problem of topology. We don't have any connectivity problem at the end, but the static topology is still a problem. It's not only about connectivity, it's how the different qubits are connected together. You can have a specific chain in your original graph that you cannot find at the end in the qubits graph. So the machine, for example here, trying to solve a literature instance of a free-sat problem, will not find end-bending, and we cannot do anything. Okay. So to conclude, this approach is to be maybe a good idea. I think it would be nice to continue to work with these specific tools from the complexity theory. I mean here the different polynomial time reduction from one NPR problem to another. And also, still on this project where we try to solve a free-sat problem, but with another type of analog quantum machine, the Pascal one. The Pascal one doesn't have static topology. The Pascal machine will create the topology according to the instance you give as input. And we already start a collaboration. We already tried this scheme, and it works better for solving the free-sat problem than to solve this problem modeling directly a qubit. Okay, thank you very much.
Thank you. Thank you very much, Samuel. So very nice presentation. There is ample time for questions. Let's say, if there are questions from online, there are no questions.
There's no one online.
Okay.
Okay. I was smiling to the camera.
I have a question actually. I'm not really familiar with quantum, only with some discussion with VR. And my question is, I heard that there is a lot of noise in the obtained results. So how can you assess this noise, and can you give the confidence interval of the result that you obtain?
This noise problem is mainly a problem you have in the programmable machine, in the universal gate-based machines such as the IBM one. Clearly here, it is already a meta-heuristic. So we have some noise problem, but it doesn't appear for the size of the problem we solved and the technology you have behind in the QPU. You have noise, but we have also noise in classical computers, but it's not the same radical problem like we can have with programmable machines, definitely. And yeah, without this noise problem, maybe I will try to present something about programmable machines. It's the noise, it's maybe the main reason why I use this type of machines, and the number of votes.
And my second, if there's no more to ask, my second question is, you have the results as probability, between 0 and 1, and how do you decide that this probability is okay to take, it's worth it to take it? Like, for instance, if you have 0.7, I mean, is there a threshold for the probability to say that we will choose this solution because the probability is high, but is there a threshold to get this this choice on? For instance,
I'm not sure to understand. To select the solution at the end?
You have the results as probability. So what makes you decide that this probability is the right decision or the right result? Because
I'm sure again, it's you're talking about programmable machines where you can have such a distribution, but here it's different.
okay,
Sorry. I think.
And yeah, let's say more a curiosity. You presented more, for example, if you compare with the first presentation, was very practical in the sense of solving like a practical problem. From what I can grasp from your presentation, for the moment, it's more the algorithmic theoretical level. But this kind of satisfiability problems, which kind of applications you see, especially where quantum annealing can perform better than other satisfiability algorithms or like constraint programming, I don't know, with programmable machines. So where do you see really the big potential maybe of this kind of application in the practical world?
Today, it's difficult to answer, but let's say the reality, to have a solution for one quantum annealing, it's one microsecond. So imagine you have a dynamic system, for example, in a port, you try to optimize tons of containers, and you have a big incident, and you need to re-optimize in very short time. Already, that can be used because directly you have a solution right now. And according to a QBO, so a generic modelization that you can update very quickly. Once you have a model to incarnate through in the instance, incarnate, I'm not sure if it exists in English. It can be very
embed, let's say maybe to embed.
Yeah.
Okay, I understand. So basically, it's really the speed is the key. So wherever you need to react very, very fast, much faster than even already the existing fast solutions with the programmable machine, this is really the key.
Today, another key, I really think it's something we finally do not consider a lot in our field, even in the different conferences. Because the way we solve a problem with classical computers, we used to only look for only one solution at the end.
Yeah.
And here we can see in this very simple example, of course, we obtain all the optimal solutions. And in many situations, I think it could be very important to have the choice. For example, if you remove one constraint, it would be nice. because it's too complicated. It would be nice to filter after all the
But
different.
these applications, let's say, as we have also said, they are very expensive. The machines are very expensive. So I think it has to be worth it in the sense that the fact that you can solve a problem in matter of microseconds makes you save a lot of money in the incident, for example, in the solution of the incident, which makes it worth spending so much money for the machines.
Yeah, it has to be like a safe for a different container.
Or saving lives, let's say, if you do
well,
something.
sure.
Okay, thanks a lot. So now the next one is virtual.
Yeah, but I don't see anyone like no one's here.
So it should be a virtual presentation
Not from what I can
called
tell.
Zakaria Bowl.
Yeah, information retrieval using domain.
Yeah, information retrieval using domain adapted language models.
So this is just these two laptops. I don't see
So no one is here.
Somebody logged in with a different name than any of the authors I saw here, and they left just a second ago.
In the schedule, there is the next presentation,
Okay,
but
so-
I think also. It's your
Yes, no, the next one is in presence.
It's
So you
presentation.
can MacArthur.
Is interactive information visualization model systematic literature review.
Yeah.
We have the presentation.
MacArthur Ortega
Ortega,
Bustamante.
right.
Can I bring it closer to me?
Sorry?
Can I bring it closer
Yes,
to me?
yes, of course.
Because I'm not wearing my glasses. Thank you.
If you prefer, you can also see.
Okay, thank
Yeah.
you. Okay. Hello, everyone. Thank you for being here. I'm so delighted to be part of the ICCSA conference. So I'm Hind Raki. I will be presenting the work done by my colleague MacArthur and our other field researchers. It's a systematic literature review about interactive information visualization models. A brief summary. We'll briefly introduce the topic, represent our methodology, and brief representation of the results, discuss a little bit of, and finally the key findings as a concluding point. So we have seen many works done by our colleagues about the interactive information systems. It's very important on so many levels, on the socio-technical level. It allows users from different fields to be able to have an interactive platform to achieve some tasks. It's used on the level of businesses, foundation, academia, etc. One of these interactive technologies is the information visualization. So, also we have recently seen fast growth of data available, the big data. So we're trying to find a generalized interactive visualization framework to have information visualization tools through dimensionality reduction. So we would like to have interactive models using DR techniques, which will be available for different users from different fields. So in order to do this systematic review, we have followed the following steps. First, we have our research questions, and then we've done the search in literature, selection of articles, and then the data extraction. The main three questions are which interactive IV models have been developed specifically for DR purposes, which information visualization techniques are commonly used to represent DR, and what are the most widely adopted methods of DR in AV. We focused on three main databases, the IEEE, Springer Link, and Web of Science. And while searching the search string, we focused mainly on these two keywords: data visualization and dimensionality reduction. For selecting the articles, it was based on three phases: the inclusion and exclusion criteria, criteria related to the search string, examination of introduction, and conclusions as a last step. And then finally, we've been able to extract data from the articles according to our research questions. So the total number of collected papers first is, as you can see, and then by the end, we've got like 52 articles to work with. So the number of articles, from 2016 and 2022, as you can see, the articles that are focusing on DR methods are not necessarily the same ones that are focusing on information visualization. Although we can see a growth of research focusing on these methods between 2018 until 2021, kind of. While inspecting the literature, the DR methods that are found in works, as you can see, are represented in this pie chart. Some other works, they proposed a different framework that integrates machine learning tools with visual analytics as ICCSA, regression, Foursquare, etc. For the strategies of navigation, we have kind of two different types: navigation strategies and visual interaction strategies. So we can conclude that we're gonna try to answer briefly the three questions: which interactive IV models have been developed specifically for the R purposes? As you saw in the previous figure, most articles do not explicitly refer to interactive IV models for the R. Filtering has been the most used visual interaction strategy, and rearranging and remapping are the least used ones. For our second question, which information visualization techniques are commonly used to represent DR? Deploying IV techniques such as scatter plots, word maps, heat maps, and ICCSA, cluster separation, and persistent homology. What are the most widely adopted methods of DR in IV? PCA is the most used one concerning DR methods. It represented 16%. TSNE comes in a close second by 14%. And the methods are often modifications of existing techniques. And we can also conclude that there is a growing trend of developing new DR techniques within the literature. Some key conclusion to take, a message to take home. So the research studies are more oriented towards information visualization techniques than interactive models for DR purposes. Since 2020, there has been a growth in articles focusing on interactive information visualization techniques and DR methods. Our systematic literature review highlights valuable insights and new research trends, such as proposing new DR methods instead of using existing ones. Thank you for your attention.
To me, it's more the way that the selection criteria that you use to filter, let's say, can you go to the slide? Let's say.
Okay, sure.
So here, what you do, so phase one, you explore both gray literature and scientific literature. Let's say, so you also go to reports. What is the source of your information that you use the Scopus, or you also use Google Scholar, so you can also find the reports.
we focus mainly on street databases using this code search string.
Okay, so here it's mostly scientific literature because you don't get if there are reports or technical reports which can be, let's say, more sometimes interesting because it's applications of, for example, industrial applications you could have, and with this you will not find them unless then the authors of the report have also published a scientific paper in your. And then in terms of interactive information visualization, so how exactly the models you explore are interactive? In which sense, like there is the required human intervention for tuning parameters, or what is the interactive component?
The interactive models that have been.
But why interactive? In which sense?
Interactive models, such in a way that are. If I got the question right, models that are like just being explored still in theory at the theory level, or they are also have been applied in different fields. Like I don't know if I got the question.
No, I mean it's just because maybe I didn't fully, let's say, understand when we talk about interactive information. The interactive stands for what? For the fact that there is an intervention of a human intervention, for the visualization of the interactive as opposed to automatic.
It can be any technology that allows the user to visualize its data.
Okay.
I just want to say, in my part selection, did you check, the difference between feature selection and feature extraction? Because in the methods you mentioned before, you mentioned PCA and PSB, and they are considered as feature extraction. But did you check, the trend of feature selection and feature extraction? What was the last years, which one of these two topics has more, use or development?
We investigated DR in both aspects, either for pre-processing steps or also as for the decision making. But we didn't differentiate between both. Like we've just reported the results as a whole.
I think if there's no other question,
I don't know if so we can stop here in this case.
Yeah, in this case we can close the session.
Thank you very much for your
Thank you very much for your participation. And I think it was an interesting display of applications and techniques. Thanks a lot.
Thank you.
Yeah. This is yours.
Yes, thank you so much.
And I have an extra USB here.
It's the one that was being.
This one was yours.
Yeah, because I got it from the conference. I don't know which one is mine.
I'm pretty sure it's this one because I remember putting it in that slot. But
It's okay because it's just.
let me check again. Is that right?
Oh yeah, this is it.
Yeah. Thank you. This is yours.
Thank you.
Thank you. So, I found what you said very interesting because I'm interested in quantum computing. And I lost a little bit in the end because I was trying to realize the game of the rooms, but I didn't get the part where you said that when you try to run the program, there is an algorithm that needs to be run in order to make an assignment to the variables, and that takes a lot of time.
In this type of machine, the bottleneck is really you give a QBO as input, so it's a mathematical model. You can express it directly with a graph.
Yes.
Like a graph. And this graph doesn't necessarily fit in the QPU. the CPU, the quantum
Okay.
system, because you have another graph with your qubits. This qubit is connected to 6 others, and the qubit is connected to others, and it doesn't match from what given input. So the machine, during the process of embedding, we try to find a way to transform your graph into another graph embeddable in this qubit.
So what I was trying to understand is whether this is an actually hard computational problem in the process, or if it's a problem of the implementation. So this is an actual computational problem that's also hard to
It's
solve.
another optimization problem, but we cannot. D-Wave does it with a heuristic by itself, and to anticipate that. For example, I try to use this reduction because I want a more sparse graph, a graph more easy to embed, but still it's not enough.
So is this still a hard problem?
The problem of embedding.
Yeah.
I'm not sure to check, but I guess.
Because it's fine if you can't, so if you have this as a bottleneck, whatever you do to handle it still doesn't matter.
No, what you can do before is to anticipate that. It's exactly the point of this work. It's to give to the machine a graph more embeddable and to have an embedding process more easy to do. And it's definitely it's a problem, but still, in quantum computing, you have several machines taking as input qubits.
Yeah.
This one, D-Wave. I don't think D-Wave in the future will continue for a long time, I guess.
I see.
But it's not a problem for us because, for example, the Pascal machines take also qubits. You have a programmable machine, the universal gate-based machine from IBM, for example.
Yeah.
So we can implement algorithm, and one of the optimization algorithm named QAOA takes also qubit.
Okay.
So all the work we are doing with qubits today, even if we don't select the right machine, we don't know. Maybe the way we work, I don't know. But anyway, the work is not for nothing because if one machine will work one day, I think qubits will be still used for optimization.
Okay. You know, because this is that in my mind, we want to make the reduction, and you know that MI maximum independent set is we have an algorithm for it. In my mind, this is where it stops. Okay, we have it.
Usually, the reduction like that,
Huh?
this type of reduction is used to state the complexity of the problem, not for solving more efficiently, but just how I finally did that. I tried to work directly on the graph to change it a little bit in order to have something more embeddable, and finally I had something very close to this reduction. So I tried the reduction, and finally the reduction was better for quantum computer and not for the classical computer that seems well known. Since we have more variables, of course.
Yes. It's very interesting.
It's a start. We will see if.
This is why it's interesting.
Yeah, for that. Have a good day.
You too.